Okay, so good morning to those of you on the West Coast, good afternoon to those of you joining us from the East Coast, and good evening to anyone joining us from Europe or stations further east. Thank you for joining this, the 24th of our regular series of seminars on pumping topics. This one will last about 35 minutes, so shorter than a lot of them, and this will allow us plenty of time for a Q&A session after the presentation. Let me just share the screen again and get the presentation up. There we go. Well, here's a listing of all the previous short courses we've run during the last year. If you've missed any of them, you can get a copy of the materials from our website. Use the following link, shortcourses.ruhrpumpen.com, or you can go to the website ruhrpumpen.com and follow the links in the top menu to RP short courses. If you go to ruhrpumpen.com, you get to this screen, and here is the link to RP short courses. Click on that and it takes you to this screen, which you can also access direct by typing in this. You'll see all the courses listed there, and you can click on any of them to see and download the course material. All of the previous 23 courses are up there, and I'm sure this 24th one will be up there in a few days. So here's what we'll be covering today. We'll look briefly at the OH3 pumps for cryogenic service, and then in more detail at the VS6 pumps, widely used in the liquid oxygen and liquid nitrogen industries. And then, with a change of direction, we'll look at the submerged motor pumps used in the LNG and LPG industries. As usual, we'll hold a Q&A session at the end, so please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the session, and the rest we'll address by mail in the coming days. We are recording this session and will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow, complete with the presenter's notes, essentially the script of this presentation. You'll also receive the Q&A summary from both of today's sessions. You'll see that Ruhrpumpen has a good history of supplying cryogenic pumps to users such as Air Liquide, Air Products, and Linde, amongst others. These pumps are cryogenic versions of our OH3, vertical inline pumps, and VS6 pumps, vertical multi-stage barrel. So when do we switch from conventional API designs to cryogenic designs? Well, it's below minus 50 degrees centigrade, which is minus 58 Fahrenheit for the OH3 pumps, and below minus 73 centigrade, which is minus 100 Fahrenheit for the VS6 pumps. Here are the most commonly handled cryogenic fluids: liquid oxygen, liquid nitrogen, argon, methane, and interestingly, I list propane here as well. Propane's an interesting one. It isn't really cryogenic, and it can certainly be handled by a conventional API build pump, albeit we're using low temperature steels. But you'll see later in the presentation that when it comes to propane storage, cryogenic submerged motor pumps are commonly used. So first, OH3 pumps. Well, the main reason vertically mounted pumps are used in cold and cryogenic service is the mechanical seal. Icing around the seal, especially on startup after being stationary for a while, can rip the faces. A methanol quench is often used on cold, but not cryogenic services. In cryogenic services, vertical mounting and incorporation of a warm-up chamber provides a good environment for the mechanical seal. Thrust bearings are regular angular contact bearings, oil lubricated. The radial bearings are product lubricated sleeve bearings. And all these are mounted in a heavy-duty mounting frame with a drain pan. Here's a sectional view of an OH3 pump. Obviously, this view has been rotated here in order to fit the slide. It should be vertically shown. Here's the suction, which would be at the bottom. Here's the impeller. Here is the sleeve type radial bearing. And here the warm-up chamber before it gets to the mechanical seal. And it can be a conventional mechanical seal, seeing near ambient temperature fluid. The general arrangement drawing, you see the motor here at the top and a flexible coupling, spacer coupling, mechanical seal, the warm-up chamber, and the casing. And a rigid frame for it. Nice photograph of that system there. I'm reliably informed that there is a pump in there somewhere amongst this Christmas tree of piping. Now, I'm temporarily at a loss to understand why we have 3 sealing system reservoirs. If any of you have any ideas, use the Q&A button and write it down for me if you know. Otherwise, I'll get an answer from the product manager in the coming days and get back to you all. Part 2 of this presentation now, vertical multi-stage pumps type VS6. This is a Ruhrpumpen Sulzer factory speciality and has been for over 40 years. Here we see how the cryogenic build pump differs from the conventional pump. Thrust is taken in the motor, so we have a rigid, axially split muff coupling. It maintains close tolerances and it's a spacer design, so the mechanical seal can be removed with the motor in place. The mounting plate can be here for a cold box design, or more commonly here below the nozzle head. Expansion or warm-up chamber. This ensures you get ambient temperature fluid at the seal. You'll see that better in the next slide. And here you see a throttle bushing to break down the pressure, which is at full discharge pressure here, down to suction pressure at this stage here. The line shaft bearings, the bowl bearings, are bronze-backed Teflon, BUB, they call that. And these are self-lubricating and they can run dry for short periods of time. Drain, we show here an external drain at the bottom of the barrel, but quite commonly it will be a dip tube type coming down here inside the barrel alongside the pump bowls. Now, as we are pumping a clean fluid, liquid oxygen, liquid nitrogen, wear rings are integral rather than replaceable. There would be a risk of them loosening during warm-up and cool-down if we were to have removable wear rings. So we avoid that and use integral wear rings. Here's a better close-up view here of the throttle bushing. It's the throttle bushing with bleed off here back to suction. So that's why we have suction pressure going into the warm-up chamber here with the bellows there. And ambient or near ambient temperature gas going into the seal chamber. And all this is achieved without an external heating source. Just ambient temperature is enough to bring the liquid oxygen or liquid nitrogen up to ambient temperature. As you can see in this photograph, and a few more photographs which I'll show you later on, we can see how effective the warm-up chamber is. We see ice forming in this area around the suction and discharge nozzles, which is here. But here in the warm-up chamber, around the warm-up chamber, so around here, it's already no ice. We've got ambient temperature just a few inches above the nozzle head. Here are the materials of construction. The fabrications, the nozzle head and the suction barrel, 304 stainless steel usually. Can be 316 if you want, it's more expensive. The series case, the bowls, 7030 cupronickel. We're not worried about corrosion. We're pumping clean, non-aggressive fluids, and so cupronickel is a good material. It keeps its ductility at low temperatures and is well machinable. Similarly, bronze impellers, perfect for liquid oxygen. When we go to hydrocarbons, we're looking at 316 stainless bowls and 304 stainless steel impellers. Again, could be 316 impellers. Shafting, nitronic 50 or Cayman L. And the bolting also, Cayman L, nitronic 50. For sealing, for mechanically sealing, well, there are 4 normal options on sealing. First is a labyrinth type seal, a gas injection seal. So the nitrogen gas is injected just above suction pressure through a labyrinth flange installed in the nozzle head just below the coupling. Here. So it's injected here. The injected nitrogen warms up the product prior to exiting, and an RTD connection is provided at the seal flange so you can monitor the effectiveness of this flange. Any reduction in temperature, drop in temperature, will indicate not enough nitrogen being injected or that the throttle bushing is worn out. Second would be a single dry gas seal with a nitrogen purge. Nice simple sealing system there. Thirdly, a double dual pressurized dry gas seal with a Plan 74 nitrogen barrier. There, double back-to-back seal with nitrogen barrier. And here's the Plan 74 gas injection. And finally, and far less commonly, a dual pressurized wet seal with Plan 53. Now, this is not used nearly so often on cryogenic pumps. There's a concern that the barrier fluid, the buffer fluid, can contaminate the pumped fluid. But some customers prefer it, and so it is one that is sometimes used. This is an educational presentation and not just a Ruhrpumpen product placement, so it's important to talk about other solutions out there in the industry. This Sulzer pumps J unit has been very successfully used in cryogenic service for wet double seals over many years. I believe the design goes back to a Bingham pumps design back in the 1960s, and Bingham became part of Sulzer. It works like this. The insulation chamber here provides a thermal barrier between the mechanical shaft seal here and the pumpage down here. Piping from the top of the insulation chamber transmits suction pressure to the J unit, the top upper portion of the J unit, forcing the piston down. This action pressurizes the sealing fluid in the lower portion of the pressure chamber, and the resultant pressure is transmitted to the seal chamber. And it would be equal to suction pressure plus whatever this spring pressure is. The pressure differential between the insulation chamber and the seal chamber, prevents there being any contamination by the pumpage or escaping to atmosphere, and provides the ideal operating environment for the mechanical seal faces with regard to temperature, pressure, and lubrication. To facilitate cooling, the sealing fluid is continuously circulated by means of a pumping ring on the mechanical seal. Well, this is what I just said. You can digest it at your leisure later on when you get your copy of the presentation. Any grease or oil coming into contact with oxygen is a potential fire risk or explosion risk. Pump factories are not traditionally oil and grease-free environments, so the Sulzer factory has a clean room for pump assembly of LOX pumps. It's air-conditioned and a positive pressure system, so no factory air gets inside the clean room. I mentioned this earlier. The mounting flange can be here or here. This second position allows the whole pump to be installed in a cold box, which enables the pump to be always ready for startup. Just a couple of photographs now. Here we have some pumps undergoing a cold spin test on liquid oxygen. So the flow is coming in through the drain connection, down and up through the pump and out of the vent connection. Again, you can see how ice formation stops directly above the pump nozzles. And here is the warm-up chamber, completely ice-free. And same again here. Ice around the nozzles, nothing around the warm-up chamber. And here, same photograph I showed you earlier. And here is Ruhrpumpen's latest customer for liquid oxygen pumps. Space rockets burn liquid oxygen and hydrogen. The liquid oxygen charging pumps at this launch site are by Ruhrpumpen. Well, part 3 of this presentation is about submerged motor pumps used in the LNG and LPG service. Now, Ruhrpumpen doesn't make this type of pump, so again, we're emphasizing the educational aspect of these short courses. The LNG liquefaction cycle is very topical at the moment, with the war in Ukraine impacting gas supplies to Europe and reinforcing the role of LNG. In the liquefaction process, natural gas is cyclically compressed and cooled until it liquefies. This results in a very high pressure product that's not suitable for storage or transportation. It will be too expensive. So the pressure has to be lowered to atmospheric pressure. And this is done by passing it through a Joule-Thomson valve, a JT valve, or more commonly now through a cryogenic expander, which is similar to a reverse running pump. So this takes the pressure down and results in liquefied natural gas at -160 centigrade and at atmospheric pressure. And this can be economically stored, transported, and later regasified. So why do we use a submerged motor design? Well, a conventional external motor with mechanically sealed vertical pumps, type VS1 or VS6, well, they present risks and problems due to the design. The seals might leak into the atmosphere. The couplings may lead to misalignment. You've got minus 160 degrees centigrade inside the pump. You've got plus 40 degrees centigrade above the pump. You've got the potential for misalignment. Bearing lubrication needs to be considered. And of course, the motor must be explosion proof. Finally, regulations require top entry only into a tank or vessel. No side entries are allowed. So that's why we consider a submerged motor design. You've eliminated the shaft seals. There are no mechanical seals here. No alignment problems. It's a compact design and it's all inside the pressure vessel. No bearing lubrication system required. Bearings are product lubricated. Noise is no longer an issue. Your motor is inside the pressure vessel again. So this one might surprise you. An explosion-proof motor is not required. And I can see some of you would think, well, surely LNG, LPG, this is flammable material. But yes, it is, but only in the presence of oxygen. And with this design, there's no oxygen and no possibility of oxygen getting into this, into the pressure vessel. They're high efficiency. The motor is high efficiency because of its cryogenic temperatures. Closer you get to absolute zero, at which there is no resistance at all, electrical resistance. Well, at minus 160, electrical resistance is reduced considerably, and so the efficiency of the motor is higher than one that is operating at 30 or 40 degrees centigrade. The pumps are tested on the actual product pumped, LNG or LPG most usually. Most pumps, of course, are tested on water. Because this is an electro-submersible pump and this motor is wet, the fluid passes through the motor, you can't use water, can you, there? And therefore, it's essential that we test it on LNG or LPG. Let me just show you the flow path through the pump. It comes in through the suction nozzle here, down outside the through the barrel, turns around and comes in through an inducer here, and then a first stage impeller. There might be several stages of impellers. Discharges out here through a diffuser and up alongside the motor housing and out of the discharge nozzle. A small amount of flow passes through the wearings, lubricates that bearing, passes through the motor, cooling and lubricating the windings. Top bearing there, again lubricated by the product, and it exits here and comes back to suction. So who makes them? There are three main suppliers: Elliott-Ibara and Nikiso. Both of these make the in-tank pumps and the suction vessel mounted pumps. And the third player is Shinko, a Japanese manufacturer, who make cargo pumps and have cornered the market for the cargo pumps, the ones that go inside the LNG carriers, the ships. So Elliott and Nikiso split the in-tank and suction vessel mounted pump market 50-50. Elliott used to make all the cargo pumps, but they've lost that business now to Shinko, who have taken 90% of the cargo pump market. Let's look at the whole LNG cycle. This is an LNG liquefaction plant. The main LNG shipping pumps are high flow, low head pumps, transferring the LNG to the atmospheric storage tanks. The in-tank pumps, here on the right, export the LNG to cargo tankers at these jetties. The LNG carriers have 4 big tanks in the hull, each with 2 cargo pumps to discharge the LNG when they get to their destination. And the destination is a regasification plant. So the LNG carriers here discharge the LNG using their onboard cargo pumps to the storage tanks in the regas terminals. These storage tanks will have 3 or 4 in-tank pumps in each one, and these feed the high-pressure send-out pumps here, which pump the LNG through the heat exchangers and which regasify the LNG using seawater as the heat transfer fluid. And from there, they go out into the grid. For smaller terminals that don't justify a full-scale land-based terminal, we have floating storage and regasification units, FSRUs. The principle's the same. An LNG carrier moors up alongside, it pumps it into the storage tanks on the FSRU, and the FSRU has a regas module here, which has high-pressure send-out pumps and heat exchangers. Let's look at the in-tank pumps. Now, regulations forbid any wall penetrations through the wall of the vessel. All connections need to be above the liquid level, so the pumps have to go in at the top. These tanks are typically 80 to 90 meters in diameter and 40 to 50 meters high. So a vertical line shaft pump is not a viable proposition. Here are some of the problems. 40 meters of shafting and column pipe, 3 meter lengths, with 1.5 meter bearing spacings. That's an awful lot of shafting to be able to handle at the top. Line shaft bearing lubrication, well, 40 meters is too long for self-lubricated bearings, so it would have to be an enclosed type line shaft. Enclosed and lubricated by what? The practicality of handling all this shafting and column piping at the top of a 40-meter high tank for installation and removal for maintenance. You'd need a Plan 53, double seal with Plan 53. You'd have a reservoir up here at the top of a 40-meter high tank, and that needs weekly top-up. A pump of this size and length would need to be at 4-pole speed, so it would be large diameter and a multi-stage pump. And the size of the motor, thrust pot, nozzle head, well, I think that would be a bit of a wind issue at the top of a 40-meter high tank. So that's why they use submerged electric motor pumps. You've got 4 columns here, each with a submersible pump lowered into each. These columns are 24-inch or 30-inch is in diameter, and these pumps are sized to slide down inside those columns. There's a spring-loaded foot valve at the bottom, so when the pump is installed, its weight opens the spring-loaded foot valve, and when the pump is removed for maintenance, it closes again and seals the tank. Here's a typical in-tank pump. Here's the foot valve in purple. And it's a nice compact design. It can be done at 2-pole speed with 1 or 2 stages, and it fits nicely inside a 24-inch or 30-inch column. Let me take you through the components, if you like. The purple bit here is the foot valve, which seals here at the bottom. Here is the pump, which again seals at this point here. There's a gasket there. And the flow comes in through the bottom, through this inducer. First stage might be 2, possibly even 3 stages. Discharges into the diffuser, and then up here alongside the motor housing and up the inside of the column to the surface. Small amount of flow passes this way through the, lubricates the bearings, cools the motor, lubricates this bearing, and is returned back down to the suction. Here's the electrical connection. The cable will run all the way up to the surface. So that's here. And here is the lifting mechanism for raising or lowering the pump into the tank. And you can just about see that in that picture there. So typical duty, 550 cubic meters an hour at 250 meters head. And I'm sorry, I didn't convert that into gallons. You'll have to do it. So here's a typical high pressure send out pump. For a land-based system, that will be about 400 cubic meters an hour. If it's going to an FSRU, probably half of that flow, more or less. So again, the flow comes here, into the pump, multi-stages, could be 15 stages, discharges out the top into 4 tubes around the motor housing, which join up together at the top and discharge here. Here is the electrical connection. Here. There's the metallurgy for these pumps. Head plates and barrels, typically 304, 304L. And the flange rating of this discharge is usually about 900 pounds, can be 1,500 pounds. Diffusers and impellers and the motor housing and the pump housing are made of aluminium alloy, A356 type T6. Again, with these, we're pumping methane, ethane, ethylene, propane. Corrosion is not a consideration, not something we need to worry about. So we don't need to go for all stainless steels or duplexes or anything of that sort. We can choose materials that are good for handling the low temperature. And aluminium alloy is easy to machine, very good ductility, even at very low temperatures. And the last type of pump, the marine cargo pumps. 8 pumps, 2 in each tank, and they're fixed in place. 1 or 2 of them will be removed at each dry docking for overhaul. These ships go into dry dock every couple of years. There's also a spray pump, a baby pump, which does exactly that. When the carrier is empty and on a return journey, the spray pump sprays LNG on the roof and walls of the tank, evaporating in the process and keeping the tank cold, ready for refilling. As I mentioned earlier, Shinko have completely cornered this market by working closely with the Korean shipyards and offering a standardized product for a standardized LNG carrier. The Korean shipyards have standardized their designs and sizes of tankers to keep the costs down. An interesting technical subject here, handling the thrust when you cannot use an external thrust bearing or take the thrust in the motor as you would do on a conventional VS1 or VS6 pump. This is how Elliott Ibarra does it, and Nikiso is very similar. The upper wearing here is larger in diameter than the lower wearing. So as a result, what you've got, the blue here is discharge pressure, the yellow is suction pressure, and the green is somewhere in between. So you've got discharge pressure acting on this face and this face, but less than suction than discharge pressure operating in this area. So your net force is going to be upwards, and the whole rotor will tend to move upwards, which closes this gap here between the thrust plate and the impeller. Close that, the flow slows down in this area, so the pressure builds up in this area, and suddenly you've got a thrust reversal. It will all try and move down. So what you get is equilibrium. It floats like this and adjusts according to the flow rate of the pump, and it works beautifully. No need for any external thrust bearing. And finally, the last section of this is the electrical connections. We use a double feed through or terminal header. This is a high pressure pump. There's the suction, the discharge is there, and this is the electrical connection. The electrical cable comes through here. So this is inside the pump, and here is the terminal header or feed through. And here it is again in close up. Schott are the best known supplier of these. The light green area is glass, and it is chemically bonded to the stainless steel flange and to the copper conductor. The dark green bits are elastomers to give a degree of flexibility. So you have a dual static seal. Here is the inboard seal, here is the outboard seal. And they're static seals, and in between is room for a nitrogen purge, or nitrogen pressurization, I should say. If the inboard seal should fail, you get a rise in pressure in here. Should the outboard seal fail, you'd get a drop in pressure. So you can monitor exactly what's going on. Well, that's it for today, and indeed for the rest of the summer. We're taking a break during the summer months, the vacation time. We'll be back with more short courses at the end of August or beginning of September. I'm leaving the meeting open for a little while, as usual, to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer will be answered within a few days. Anything you think of later, send an email to info@shortcourses.ruhrpumpen.com. Our marketing team are standing by to direct your questions or suggestions to the best person to answer them, which is probably going to be me, and they will be sending you the YouTube recording and the PDF of the presentation. Should you need a certificate of completion for this course, again, info@shortcourses.ruhrpumpen.com, and they will sort it out for you. Here, right at the end, before we get to the Q&A, are 8 slides about Ruhrpumpen that remind you of who we are and what we do. Well, they'll be in the PDF copy that you get of this presentation, so you can peruse them at your leisure. You don't need to do that now. So, on with the Q&A. Let me stop the share and see if we have any questions, and we do. We have 12 at the moment, I think. So let's have a look and see what we've got. Carl Hogue says, how much flow as a percentage of total pumped goes through the buffer bushing? It's a tiny proportion. It really is a tiny proportion. Almost unmeasurable. It's just, I'm assuming you're talking about the one in the LNG and LPG pumps, the percentage that goes through to lubricate the bearings. 1 or 2 cubic meters an hour max. Roberto Carmona says, is there any use for polymeric materials on radial bushings, such as Viton, Vespel, or similar? being this is clean service. The low temps may be a limiting factor, I would think. Yeah, the gaskets that are usually used in these are stainless steel gaskets with filling. It's gone. Name's gone from my mind. The usual gaskets that is used on hydrocarbon pumps. Nathan Little says, liquid ammonia is becoming a very popular application. Can it be assumed that ammonia would be treated as a hydrocarbon for pump design and sealing? Yes, but interestingly, Elliott Ibarra do have a design that of vertical in-tank pump that has magnetic driven motors, and so it's a similar design to their in-tank pump that they use for LNG, LPG, except it has a nitrogen purged motor operating through a magnetic coupling. Speak to your Elliott Ibarra local rep, and he'll talk to you about that. Heidi Berger says, what is the liquid in the submerged LNG LPG pump? It's the pumped product, either LNG or LPG. It passes through the motor as well. Carl Hogue says, when did Elliott Ibarra first develop the thrust bushing? About 40 years ago. It was at the time that they developed the vertical submerged motor pump. Anonymous attendee, does Ruhrpumpen have any plans to get into the in-tank pump market? Well, you should never say never, but it will be a big step. It will be a big step to break into that very established market. Anonymous attendee has said, very informative, love your seminars, keep up the great educational work. Oh, thank you very much. I like that. Another anonymous attendee, I'm an ex-ACD and worked on fluid dynamics. Can you please explain the effect of NPSH and cavitation on pump selection? Well, I've done courses on NPSH already, and I think I'd sooner refer you to what those. If you look at the list of short courses, there is a course in there on NPSH, and so that would be where I would best like to direct you. NPSH is an issue, especially for the in-tank pumps. That's why the in-tank pumps have inducers at the bottom to help the flow into the pump, and it's to establish the minimum possible level of residual fluid in the tank, so you can pump that tank down till it's nearly empty. Every meter or foot of liquid that's in there is lost revenue, so it's essential that it be pumpable right the way down, hence the use of inducers, which will get the level in the tank down to about 2 or 3 meters usually. Oscar Ulysses Melgar Cruz says, please share the presentation. Yep, you'll get the copy of the presentation. Everyone who has attended will get a copy of this presentation. Excuse me. Stanislav Vyasunov says, hello, what would be typical drive for LNG pump? Variable frequency or fixed rotational speed? Very common to use variable frequency drive now. They're perfectly suitable for it, and yeah, a lot of the cryogenic pumps are VFD driven. Anonymous attendee, would the cryogenic pump be recommended for cold liquid ammonia applications, -27 Fahrenheit, or would they just be standard VS6 pump? Well, you can use a standard VS6 pump. You can, and as I mentioned earlier, Elliott Ibarra have an in-tank pump that is with a submersible motor. Usually there are not the same regulations for ammonia tanks. You can go out through the side of an ammonia pump, so you can use a conventional VS6 pump as a charge pump. What are the advantages of the in-tank pumps? This is Heidi Berger. Is it only to avoid any side tank nozzles? Well, that's its main reason for being, is that you have to go in the top. So therefore, that's what you need. And it has loads of advantages over a VS1 pump installed in through the top, as you will have seen in one of my earlier slides. Rouvière Davis says, how do you regasify LNG at a typical installation? Thank you for the interesting training, Simon. Well, thank you, Rouvière. The regasification is done through heat exchangers, usually a plate type heat exchanger, and seawater is used. You're normally at the coast. An LNG carrier has come up to the terminal and is discharging, so you've got plenty of seawater there. And so seawater at 10 degrees centigrade is ideal for passing through the heat exchanger and regasifying the minus 160 degrees centigrade LNG. Hans Bert says, why does Ruhrpumpen not enter the market of in-tank submerged motor pumps? Private answer is also okay, if the answer is too sensible or strategic. I was asked this question when I first started working with Ruhrpumpen for these presentations. It's a lot of investment, and quite frankly, for what reward? The market is probably not big enough to take a third player at the moment. Nikiso and Ibara have it sewn up at the moment. It would take 10 years to break into that market and get a third share of the market. And with the investment in product that wouldn't be needed, it's not really viable. Nathan Little says, I'm familiar with the mag drive in-tank pumps, but does Ruhrpumpen implement VS6 pumps for ammonia? Yes, absolutely. VS6 pumps for ammonia, very common. It's one of Ruhrpumpen's major market on. It's a conventional VS6 pump with a conventional mechanical seal and a conventional surface-mounted motor, not a submerged motor. Anonymous attendee, when should a VS6 pump with normal suction versus double suction be used? What are the disadvantages of double suction VS6 pumps? Are they then called a VS7? Well, yes, you're right. It becomes a VS7 when you have a double suction. They're not very common. The double suction first stage becomes very big in diameter, puts up the size of the suction barrel, and often you'll find that the advantage is not there. When you get to very, very big VS6, VS7 pumps, then a double suction design, double volute design, double suction, double volute design could work for you, but it's not very common. Almost always a single suction design. Mugda Dokale, thank you, we'll check that out. Anonymous attendee, will the recorded webinar be uploaded to Ruhrpumpen YouTube website? Yes, it will. Might take a couple of weeks before it gets there. Facundo Ulissi, excuse me if I've pronounced it wrong. Good afternoon. On in-tank pumps, do you have more detail about supporting an erection cable? Shall the support cable be tightened prior to operation? We're getting into too much detail there on something that is not my area of speciality. You want to be talking to Elliot Ibarra or Nikiso about that sort of thing. Roberto Carmona, thanks again, Mr. Smith. As always, an enjoyable and informative session. Could you repeat the address for the certificate of compliance request? Well, it is info@short-courses.ruhrpumpen.com. info@short-courses.ruhrpumpen.com. Anonymous attendee, what is the typical barrier fluid for Plan 52 unpressurized dual seal for cold liquid ammonia pumps? For Plan 52, it could be a light oil typically, but we normally leave the selection or the recommendation of a barrier fluid to the mechanical seal suppliers, because it's in direct contact with their mechanical seals. So we take their recommendation normally. Rouvier Davis, please explain the DUB Teflon coated bearings. What does DUB actually mean? I don't know. I'll have to look that up and do it. It's a bronze backed Teflon bearing, bronze giving the mechanical strength to the Teflon bearing, but I don't know what DUB actually means. Well, that appears to be all the questions. Oh, wait a minute, there's another one here. Nathan Little says, nice selection of matching tie and vest. Thanks for that. I've got 4 of these, all in different colors. I try and circulate them. Anonymous attendee, is low temperature carbon steel or stainless steel preferred for liquid ammonia? Very good question. Low temperature carbon steel is perfectly adequate for it, but availability is very dodgy. It would be cheaper than stainless steel, but in practice, you might as well get stainless steel, which is in stock at many stockyards material, whereas low temperature carbon steel, you normally have to wait for a special order. So nice question, thank you. Also, is post-weld heat treatment common for liquid ammonia VS6 pumps? Yeah, you would normally have to do post-weld heat treatment on the welds. Certainly if it's a carbon steel, not for a stainless steel, I think. Okay. 5 to 6 here in the UK, which means it's beer o'clock for me. I'm going to pull this session to an end and say thank you very much for attending today. It's been a very interesting session for me. I love it when there are lots of questions coming at me. I hope you found it useful and my answers were helpful. I look forward to seeing you again at the end of August. So take care and goodbye.